Welcome to the ES192 Civil C11 group project. In this video, we will cover the process of the creation of our roller coaster, the calculations involved, and the final testing of our product. In the first session of our project, we had to conduct our initial brainstorming. We drafted key ideas using sticky notes and prioritized them in a graph of y-axis as impact of success and x-axis as effort required. Through this exercise, we found out that the main specifications of our design would be longest time of travel, complexity of roller coaster, design aesthetics, longevity, and material optimization. After the initial brainstorming phase, all 7 of us created sketches of what we think the design should be, and then we discussed to combine all of the best ideas into one developed design. This developed design that we had all opted for had an even balance of point accumulation, aesthetics, and material optimization. It can be seen from our sketches that we had strategically placed our truss structures at the edge of the board and that we had maximized our 180-degree turns. In our research, we also noticed that what makes roller coasters appealing is the vertical 360-degree loop, which is what we have incorporated as a way for point accumulation and design. Based on our developed designs and sketches, we created a cardboard model of what our design should look like. And now, we had to have calculations and final measurements to make the actual product. In our calculations, the main focus was calculating the minimum height of the drop before the vertical 360-degree loop. We considered friction in our calculations by dragging the ball using a force meter up an inclined wooden surface. This free body diagram will give a clear explanation as to how the coefficient of friction is calculated. By resolving the forces, we can calculate the resultant force R, and the tension, which is equal to the number on the Newton meter, is also equal to weight plus friction. This then can give us the coefficient of friction, as we already know the R value and the F value, which will be used to find the minimum height before the drop. We then use conservation of energy to construct an equation for the minimum height. From the calculations shown here, the only energies are kinetic, gravitational, and frictional. Therefore, in section 2, we found the speed before the drop in order to use conservation of energy for section 3. In section 3, we begin by taking the kinetic energy of section 2's speed and by considering the GPE of the height of one diameter of the loop. For the ball to go past the loop, the speed at the top of the ball, which is W in this case, has to be greater than 0. We then, by inspection of materials, assume that the radius of the loop is 4 times the radius of the ball and plugged in the numbers to calculate the minimum height of the loop. Based on these assumptions and equations, we found out that the minimum height is around 13 centimeters. Furthermore, the critical buckling force for the thin balsa strips that would be used as the main struts in the truss was calculated to be 1.6 newtons using P equals pi squared EI over KL squared. After figuring out the calculations and dimensions, we then began the building phase of the product. And now, we begin the testing phase. In our 3 tests, it was unfortunate that our best trial only cleared half the section of the vertical 360-degree loop. This failure can be explained with different reasons. Firstly, the table at which the testing was commenced was angled against our slope, which meant that there was not enough momentum for the ball to go up the loop. Secondly, we had tested our ball many times, which caused material fatigue and definitely did not hold up as well as it should have during the actual testing. Nevertheless, the first section still gave us a lot of points, and here is our points tally. Thank you for watching our group presentation.